So in section 1.2, we're going to take a look at signal transformations. And these transformations are going to be, like many things in EE3032, building blocks that we use to build up more complicated, more powerful systems and signals. So the three transformations that we're going to look at are time shift, time scaling, and time reversal. These are very common ones that are going to be useful to us in describing all sorts of systems. Now, what is a system? A system, from a very high level signals and systems point of view, a system T here takes some input signal, which may be a voltage applied or a sound wave coming in, and it processes it, usually through some mathematical process. It could be an electric circuit performing that mathematical process, and it produces another signal, another function of time as an output. So one example might be if you have some function x, and let me replace the independent variable here with a substitute variable, and you want to perform an integral of that. So maybe you have position, or maybe you have velocity in x and you want to get position. So if we assume that everything is zero before time is zero, which we often do in many systems, we start from an initial state where things are at rest and at the zero position, we can say, well, if I want to know at time t here, time t, what my output of the signal is, my position, maybe I take the velocity function and I integrate it over all times tau that range from the start of time, which is zero, to the current time t. So that would be an example of a system. And indeed, we're going to see a lot of integrals of this form later in EE3032. So that's an example of a system, a very useful system. But before we can get to those, we're going to take a closer look at some building block systems, some other ways to transform a function x or an input function into a function y or some output function. So let's start with time shift. So for time shift, what we do is we say that we're going to have our function y is equal to the input function shifted by some time, capital T. And what you can think of this, if you want to think of it from a mathematical point of view, we're talking about function composition. So I have my independent variable t here, and from a function point of view, I'm saying, before you tell me what the output is, take whatever the t is and reduce it by this constant. Maybe this capital T is 5 seconds. Reduce it by 5 seconds, and then evaluate the input. So this is just taking an input x, and it's delaying it by capital T seconds. When I say delay, we're assuming capital T is a positive number. If I subtract a negative number, of course, I'm going in the opposite direction, and I would be not delaying the input, but I would be making the input come sooner. So as an example here, let's say my function x of t looks like this. From 0 to 2 seconds, it reduces in a straight line from 4 volts to 0 volts, and then it's 0 volts at all the other times, and it takes 2 seconds to do that. Now, if I let capital T be equal to 5 seconds, then my y of t is going to say, well, I have delayed that to the right. So I start at 5 seconds, and I end at 7 seconds. And I have x is delayed by 5 seconds there. So what this is doing is it's replacing, if I take the function and I replace the t variable with t minus capital T, the delay, that causes a delay operation by 5 seconds. Now, if I had let capital T be -2, as an example, let's do that. Another example, capital T is -2. Well, then my output function is going to look like this. And now I have x of t minus -2 or +2. So I'm making it come earlier. I'm making the output come before the input came. Now, in real life, we can't build a circuit that does that in real time, but mathematically we can write it. We can say the output comes before the input. So when I do a time shift, I am replacing the t variable with t minus the delay. So that's our first example. Now we'll go to time scaling. With time scaling, you replace the t variable with some constant times the t variable. So what I might have here is I could say y of t is x of 2t. And what I'm doing now is I'm saying if I want to know what happens here we'll use the same function x as we did before, and I want to know what my y is now, well, I can evaluate at 0. So if t is 0, I say, okay, I want to know what happens when this t is 0. So I do function composition. I say, okay, I have to evaluate this modified time argument. So 2 times 0 is 0. And then I go and I say, well, what does the x function do at 0? It's 4 volts. So, okay, that tells me I have this point at 4 volts. Now, let's go halfway up. Let's let t be 1/2. So this t is 1/2. Then I evaluate by function composition. I multiply it by 2. So I get 2 times 1/2, x of 1. What is happening at x of 1? Well, the function has decreased down to 2 volts. It's gone halfway down there. So at 1/2 of a second, I have decreased to 2 volts. So, and if I go up to t is going to be 1 second, then the argument in x here, 2t is 2 seconds, and that's when it decreases all the way down. So there's a few points. It's making a straight line there, and it's 0 outside of this range of 0 to 1 second. So what happens is when I have this compression factor A, which is 2 in this case, when I have A has a magnitude greater than 1, we call this compressing time. Compressing time, or time compression. I've made the function occur faster or at a more compressed amount of time. If you let this factor be something like 1/2 or 1/3 or 0.7, you're expanding time, you're slowing down the function. So if the magnitude of A is less than 1, then we have time expansion. Okay. I'm going to go to a new slide here to make us room to talk about time reversal, and then we'll put it all together. So we have time reversal now. On the last slide, I didn't say what happens if A is negative, and that's kind of covered here by the time reversal case. So let's recall, let's use the same function x as a model. I have something that takes 2 seconds to decrease in a straight line fashion from 4 volts to 0 volts, and we're calling that our function x for our example here. Now, time reversal is when you have y of t is x of -t. So my transformation here is I have replaced all the t's with -t's. And when you do that, you end up flipping the time axis, and I get this value right here that's happening from -2 to 0 seconds for y of t, since I've reversed it. Now, let's try combining a few steps. Let's say I start with my function x of t, which is the same as before, like this, and 0 elsewhere. And let's say I do the following two steps to it. First, I delay it by 4 seconds. So I get this function. It's going to start at 4 seconds and end at 6. And that'll be 4 volts there. And why don't you pause the video and see if you can write the expression for what this y of t is if it's x delayed by 4. So go ahead and pause. Okay, let's see if you figured out what the right answer. If we're delaying it by 4, we have t minus 4 here. So let's do that. And now let's do this. Let us do time compression by a factor of 2. So when I do time compression by a factor of 2, let's do it graphically first. We'll call this function z, because I've already used x and y. And what I do is I take the function y, and I'm going to compress it by a factor of 2. So z of t, I'm doing something to the intermediate step. So I take y here, I speed it up by 2. And when I get to 1 second, well, then I have to look at what y is doing at 2 seconds, so it's 0. When I get to 2 seconds, I have to look at double t, so I double it and I say, well, what is the function y doing at 4 seconds? So I go from 2 here, a says double it, so I go to 4 seconds, and that's where the function jumps up. So my function z here is jumping up to 4 volts at that time. And then before it took 2 seconds to decay, but now I'm scaling time up, so it only takes 1 second to decay. So this takes me from 2 to 3 seconds, and I do that decay. So let's put this all together and have the multiple transformations be in our equation. So if we want to put z in terms of x now, so we have z of t is y of 2t, and that is equal to y is equal to x at t minus 4. So we have 2t minus 4. So what we've done is we have it in this form, and we note that if I rearrange this a little bit, if I factor out the 2, like so, this here is my time delay. So I started with a time delay of 4 seconds, but since I did that first, when I did the compression, it got compressed to a net delay right here of 2 seconds. So my first step was delay by 4, and then I compressed, so by 2. So if I want to think about writing it as I just said it, that I delayed by 4, and then I compressed by 2, we get this form right here. I get the equivalent form if I just factor out what's going on inside that argument by saying I have two things going on. I have a compression by 2. I'm speeding up time by a factor of 2. And if I consider what was happening at time 0 in the original waveform, I have delayed that feature by 2 seconds. So the feature at 0, that's often important to feature at 0, that's usually where the signal starts or where the input turns on, that feature has been delayed by 2 seconds in this example. So this is very easy to mix up the order when you have two operations like this. So if you're ever in doubt, and you just work it through. If I want to know what's happening, say at 2.5 here, to make sure I have it right, I say, okay, I want to know what's happening in function z at time 2.5. So this t right here is 2.5. So I let that t be 2.5. So 2.5 minus 2, if I look at it this way, okay, so that's a half times 2, that's 1. Then I have to look up what's going on at x at time 1. And x is halfway through, so it's down to 2 volts, just as it is here. The other way I could look at it is this form, right? These two forms are equivalent. So if t is 2.5, then this is 2.5. And I have 2.5 times 2 is 5. Minus 4 is 1. We get the same thing as we would expect. So x of 1, again, I'm back here, and I'm halfway down my voltage ramp. So my advice to you is be careful. And when you do a transformation like this, when in doubt, always plug in the time at the function you're evaluating into the expression and see what it does. I'm mapping back the original function x to my ultimate function z. I can combine this all with time reversal. So if I made the a here -2 instead of 2, then I would have also time reversed it. So let's do that example. So if I first delayed, I would have something coming on at 4 and off at 6 with a height of 4. And then I would say, if I do what a is -2 now, what happens is I get a time reversal. So I'm on negative time from -2 to -3 with the same amplitude up to 4 here. And this would be, let's call that k of t is going to be x of -2t minus 4. Now, did we do that right? Well, let's factor x of -2t plus 4. Okay, so did we, no, we did not do that right. Let's see, I factored wrong, that's why. So there we go. So we have shifted it to, that was 2, right? Sorry. I have shifted it, I have advanced it 2 to the left, and I have also compressed it, so it's happening here. That drawing is a bit sloppy. I have moved it 2 to the left, and it goes off at 3. So my original drawing was wrong there. Okay, so this is section 1.2 on time shift and time scaling and time reversal. What I'm going to do is I'm also going to post a MATLAB file that you can run in MATLAB. You can download MATLAB from the Software Center if you don't have it from a class last year, and it will create these graphs for you, and there'll be some comments in there, and you can experiment with these transformations a bit. This is an extra thing. The MATLAB features are not required for what we're doing in the class right now, but I will post that, and that will give you an opportunity to interact with this example a bit.